and welcome back to another RUS Copernicus webinar. My name is Miguel Castro, and today I will be guiding you through this topic. Today we're going to be having a look to the pollution over the north of Italy using Sentinel-5p data. So, a few words before we start this session. I would like to highlight that this webinar is going to be run using Python. So, if you are familiar with the RUS webinars, this time we will not be using Snap, but Python this time. So, before starting, let me tell you the objectives of this session. Today you will learn two main things. First, how to monitor pollution using Sentinel-5p data. And second, what is the RUS service and how it can help you in your projects with Copernicus data. So just before starting, be aware that this webinar is being recorded and that you will be able to repeat the exercise by yourself later on using the cloud resources of RUS Copernicus. So before starting, let's very briefly have a look to the outline of this session. We'll first of all introduce the RUS Copernicus service so that you know the potential advantages that this project can bring you to your Earth observation projects. We will then describe in detail the Sentinel-5p satellite, its characteristics, and we will go into the details of the data files that we are going to be using today. We will then run our exercise, as I said, using Python this time. And at the very end, we will have some time for a Q&A session. In total, the webinar should last around 1 hour and a half. So let's get started. And as I said, let's start by describing the RUS Copernicus service. So as you may know already, RUS stands for Research and User Support for Sentinel Core Products. It is an initiative founded by the European Commission and managed by the European Space Agency with the objective to promote the uptake of Copernicus Sentinel data and support your R&D activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines. Using the virtual machines, you will be allowed to handle and process the data derived from the Sentinel satellites. So in other words, what do I mean by that? Well, with the large amount of data produced by the Sentinel satellites, the challenge in Earth observation is no longer data availability, but rather storage and processing capacity. To solve that, RUS Copernicus offers virtual machines so that you can have the appropriate computing environment to handle the data. In addition to all that, RUS also provides specialized user help desk to support your remote sensing activities with Sentinel data and a dedicated training program that's from which this webinar is part of. So you can find all the details and all the full information about the project in our two main websites. So I recommend you to check them whenever you have time after this webinar so that you can get familiar with the project, its characteristics, and the different options you have to exploit Copernicus data. So let's jump now into Sentinel-5p and let's have a look to this Copernicus mission. Oh, by the way, before I do that, I forgot, I would like to highlight that we have the YouTube channel. So here you will find all the previous recorded RUS webinars, and it is also here that you will find the recorded version of this one in a couple of days. So as you can see, we have many topics already, and I'm sure you can find something that might be interesting for you. So as I said, let's go and have a look to the Sentinel-5p mission. So Sentinel-5 Precursor, or Sentinel-5p, is the first Copernicus mission dedicated to monitoring our atmosphere. The satellite maps a multitude of air pollutants around the globe. Launched in October 2017, Sentinel-5p reached its routine operation phase in early 2019. It aims to fill the data gap and provide data continuity between the retirement of the Envisat satellite, the NASA Aura mission, and the launch of the upcoming Sentinel-5 satellite. The satellite carries the state-of-the-art Tropomi instrument to map a multitude of trace gases that we will have a look later. So some details about the technical characteristics of the missions. In this occasion, we have a single satellite mission. So if you compare this to Sentinel-1, 2, and 3, which are missions that are formed by twin satellites, so two identical satellites orbiting at 180 degrees to each other. In this case, we have only one satellite, which has a swath of 2,600 kilometers. It has a daily revisit time and a spatial resolution of 7 by 3.5 kilometers. And it follows, as you can see in the animation, a polar sun synchronous orbit in loose formation with the Suomi NPP mission from NOAA. And this is actually a very key aspect of Sentinel-5p. What loose formation means here is that Sentinel-5p orbits 3.5 minutes behind the Suomi satellite, and the reason for that is that the Suomi provides a collocated high-resolution cloud mask, which is very important for calculating some of the level 2 products that Sentinel-5 provides. So let's now talk about the instrument carried by Sentinel-5p. So what sets Tropomi apart, or Tropomi, by the way, means the, as you can see on the slide, the tropospheric monitoring instrument. So what sets Tropomi apart is that it measures the ultraviolet and visible near-infrared and shortwave infrared spectral bands. This means that a wide range of pollutants such as nitrogen dioxide, ozone, formaldehyde, sulfur dioxide, methane, and carbon monoxide can be imaged more accurately than ever before. Let's move on then to the different data products that are produced by Sentinel-5p. The data products from Sentinel-5p instrument are distributed to users at 2 different levels, and it's very important for you to understand the differences so that you know when you have to download the data which one you should pick. So on one side we have the level 1b product, which provides geolocated and radiometrically corrected top of the atmosphere Earth radiance in all spectral bands, as well as solar irradiance, and is the main input for the level 2 processor. So in the level 1b product you will find the actual measurement done by the instrument that is carried in Sentinel-5p. On the other hand, we have level 2 product, and this is the one that you will be more interested on. So level 2 provides atmospheric geophysical parameters. This is the product, as I said, that the product type most of you as regular users would be interested on, and is of course the product level we are going to be using in this webinar. So in the level 2 you will find the products that use level 1b information to derive the different concentrations of the gases that are measured by Sentinel-5p. So in this list you can see the full list of level 2 products. So on the left side of the tables you can see the acronym that is used to describe that product type, and on the right side the name or the short name of the parameter that is retrieved. As you can see, there are different products for ozone. There are also you have the level 2 product for nitrogen dioxide, carbon monoxide, etc. So as you can see, very extensive list. So the last technical aspect I want to share with you about the mission is the timeliness of the data. This is another key aspect that you need to understand when working with this mission, as you will have to define this parameter when downloading the data. So Sentinel-5p data can be delivered to user, or is being delivered to users by ESA in 3 different timelines, let's say. You can find products in what is called the near real time. So this is mainly to be in line with the needs of numerical forecasting systems, and it only applies to level 2 products, which are to be supplied within 3 hours after sensing. So 3 hours the satellite acquires the product, it is made available mainly for these numerical forecasting systems. And remember here, you will only find level 2 products you will only find near real-time products for level 2 products. On the other hand, the second option we have in terms of timeliness is the non-time critical option, which is formed by the offline products. And the offline products takes advantage of increased accuracies achievable when specific calibration steps and trace gas retrievals are performed with relaxed timing. So they are made available, as you can see, for level 1b and level 2, and depending on the level, you will have the products either 12 hours after sensing or 5 days after sensing. And this time delay is just to make sure that higher accuracy can be achieved. Another main aspect between the level 2 near real-time products and the level 2 offline product is that the offline product will always be the full orbit of the satellite, while the near real-time will not contain the full orbit. This is something we will see later on the exercise. The third option in terms of timeliness for the data, the other non-time critical option is the reprocessing, sorry. So in this case, it is an option that is used by ESA whenever a major upgrade has to be done to the data due to a change in the algorithms that are used to derive level 2 products. And this is something that happens whenever ESA or the scientific committee decides to make the update. So with that being said, let's move on. And the first thing I want to clarify about Sentinel-5p data, since I guess this is the first time, or maybe one of the first times you see these products, is their name. So as with Sentinel-1, Sentinel-2, and Sentinel-3, Sentinel-5p follows a standard naming convention. And as with the other Sentinels, it is actually very important for you to understand what this very long name of the Sentinel product means, because this will give you a lot of information of the product even before going through the download process. And whenever you have to work with a lot of data, you want to optimize your download process as much as possible. So here we have an example of a level 2 product from Sentinel-5p. You can see that at the very beginning, you will always see the name of the mission. In this case, it is a Sentinel-5p. So, and it's always going to be the case. Then it is followed by the processing string. So Sentinel-5p can be either near real-time, offline, or reprocessing. So this keyword in orange will tell you which kind of processing stream the product you are working on has. Then we have the processing level, you know already, either level 1b, so top of the atmosphere measurements, or level 2 geophysical parameters. In case, and here I'm only showing the product identifier for level 2. So as product identifier for level 2, you can see a very long list. Remember, we are measuring different trace gases throughout the atmosphere, and here you can see the acronym for each of them. Then this is followed, as in any other Sentinel mission, by the start and end of the granule, and the format of that is year, month, day, followed by a T, which is a fixed character, and then hour, minutes, seconds. Then we find the orbit number, which is an absolute number, the collection number, the processing version, and the time of processing for this granule. Those last parts of the name, most probably you will not be interested. I would say you are interested from the mission name to the start and end of the granule, but it's always good to know the meaning of everything. So with that clear, let's talk a little bit more about the data products we are going to be using in this webinar. As I said, we are going to use level 2 products, and more in particular, we will be using nitrogen dioxide, the nitrogen dioxide product. So let's go a little bit more deep into those products. So the thing you have to know about Sentinel-5p is that all the products are saved or are delivered to users as single netCDF files. So if you are new to Sentinel-5p, or if you come from the standard optical domain in Earth observation, I'm referring to Sentinel-2 or Landsat, etc., you might be used to data formats such as GeoTIFF or JPEG 2000, etc. And maybe the netCDF format is not very familiar to you, but it is the case for Sentinel-5p, and it is very important to understand the characteristics of this format to later on be able to process the data. So I'm going to briefly describe you, as you can see here on the slide, the characteristics of this format, the netCDF file, and then we will continue. So netCDF, which stands for Network Common Data Form, is a file format for storing multidimensional scientific data, which are variables, such as, for example, temperature, humidity, wind speed, or in the case of Sentinel-5p, the concentration of a specific geophysical parameter such as NO2. So each of these variables can be displayed throughout a dimension, and the dimension here can be, for example, time. And this format, by the way, is widely used in the atmospheric and oceanographic scientific communities. So as you can see, some of the main characteristics of this format is that the files are self-describing, portable, and scalable. You can see the description of those characteristics on the slide. So knowing that, you have to know that every netCDF file has a specific structure, has specific elements that form the netCDF file, and where you will find the actual measurement of, in this case, the satellite. So the four things you have to remember is that a netCDF file has dimension, has variables, has attributes, and has coordinates. So the dimension here, or a netCDF dimension, has both a name and a size, and can be used to represent a real physical dimension. For example, the dimension for time, latitude, longitude, or height. Don't worry if those concepts are a little bit abstract now for you. Later on during the exercise, we will see them together in action, and it will make more sense. But just try to get the idea. Then we have the variables. So the variables in a netCDF file is actually where you will find the measurement itself. In this case, the NO2 concentration, for example. So as it is written, it is in the variables of a netCDF file that you will find the actual measurement. And a variable represents an array of values of the same type. And variables are used to store the bulk of the data in this kind of files. And the variable, also important to remember, has a name, a data type, a shape, and is described by a list of dimensions specified when the variable is created. The two other things you need to know about the characteristics of the netCDF files are attributes and coordinates. Attributes, it's very easy. Those are, let's say, the metadata of the data. So netCDF attributes are used to store ancillary data or metadata, and most attributes provide information about the specific variable. Some attributes can be related to a specific variable, but some others are called global attributes and are used to describe the entire netCDF file. And finally, we have the coordinates, which is a one-dimensional variable, and this is very important, with the same name as a dimension. This is what we call a coordinate, and it is associated with a dimension of one or more data variables, and typically defines a physical coordinate corresponding to that dimension. So again, if you're new to netCDF file, this might sound like a lot of information. You can find a lot of references for this on the internet, but continue with me, and later on in the exercise we will see more in action those concepts. Okay, so the next thing I want to talk about the level 2 products we're going to be using is how they are structured. So you see, when you work with the netCDF files of Sentinel-5p, you will find that the product is organized in different groups. So working with this data, you will see that different groups are used to organize the data and make it easier to find. So the outermost layer is the file itself, and then two groups can be seen, the products and the metadata group. And both of them contain, at the same time, subgroups. So why I'm telling you that? Well, because once we start to play with the data, we will have to reach our variable that contains the measurement, and we will have to navigate through the different groups and subgroups of the product. So you need to know that this is the way the level 2 netCDF files are organized. So for example, you can see that within the metadata group, we have a subgroup that's called, for example, algorithm settings, and there you can find some attributes. And we know already that attributes means, let's say, metadata. However, for example, in the product group, we can find variables directly, we can find dimensions, but also we can find subgroups that contain at the same time more variables. So very briefly, what is the product and what is the metadata group? So the variables in the product group will answer to the questions what, when, where, and how well. This group stores the main data fields on the product, and include the position of the main parameters, the latitude, the longitude, etc. So one thing that is very important to know in this product group is that it is here where you will find the QA value parameter, and we will come to this later on, but I want to introduce it now. This is very important because it summarizes the processing flag, the processing quality or the processing flags into a continuous value, giving a quality percentage for every pixel. 100% is the optimal value and 0% is a processing failure. And you have values that range from 0 to 1 or from 0 to 100%. Then we have the metadata group, which is just a group that collects metadata items required by metadata standards. So the thing I want to highlight in this slide is, as you can see, the structure of the file. But please, if you are going to work with this data, I really recommend you, and it is a must if you want to understand properly the data, to go through the technical documentation made available by ESA on the Sentinel-5p ESA website. So you will find there a couple of, I think there are 5 technical documents describing the data and everything related to this product, including the algorithms that are used to retrieve those geophysical parameters. So I really recommend you to at least go through the product user manual. So I'm leaving you here a screenshot of the beginning of this document, a link that you can go. If you just Google the name of the document, you will also find it. It is here where you will find the description of this file structure and the meaning of everything. So please do check this document. It will make your life easier when working with this data. Okay, so that's all for the introduction of the Sentinel-5p mission. Now let's focus on our exercise. Let's start to do something. So what are we going to do? Well, the objective of this exercise, of this demo, is going to be to assess the decrease of air pollution caused by the lockdown in the north of Italy due to the COVID-19 outbreak by analyzing the NO2 average concentrations in March 2020 compared to March 2019. And how are we going to do that? Well, we will do it using as framework a Jupyter Notebook, more precisely a Jupyter Lab. Then within this Jupyter Notebook, we will use Python to run our analysis using 2 main libraries. The first one is going to be the xarray library, which will allow us to process netCDF files in Python. The other library is going to be HARP. HARP is not actually a Python library, but it's a software that I'm going to introduce you now. But this HARP software is going to allow us to pre-process our Sentinel-5p data and bring it from level 2 to level 3. So don't worry, I will go very deeply into this later on, but just to give you an overview. So now that we are talking about the tools you can use to process Sentinel-5p data, I want to give you very briefly an overview of the options you have in the RUS Copernicus virtual machine. So if you are more into a graphical interface setup instead of a programming one, such as the one we're going to be using today, you can use the ESA atmospheric toolbox. So if you are coming from Sentinel-1, Sentinel-2, or Sentinel-3, you might be familiar with Snap. However, if you want to work with Sentinel-5p data, Snap is not the software to go. It doesn't mean that ESA is not giving you any option. It is actually. So there is the ESA atmospheric toolbox, where you can see here a very brief description of it. And the important thing here is that the project consists of several software components, and the main ones are CODA, HARP, and Vision. And today we will be using HARP, which is part of this atmospheric toolbox. So the good thing the thing to remember about HARP is that it will allow us to ingest, process, and by doing that, intercompare satellite data. And the thing you have to know about HARP is that the toolset provides a set of command line tools, so you can run it from command line, but also a library of functions that can be directly used from an interface in Python, or as you can see in IDL and MATLAB. So it is up to you to choose the interface you prefer the most. I'm giving you here the links to this software, so if you're interested, you can have a look. By the way, if you're interested to learn how to process Sentinel-5p data in a more graphical way instead of with Python as we will do today, I recommend you to check our previous RUS Copernicus webinar on this topic. We did it a couple of months ago. It is called Air Quality Monitoring with Sentinel-5p. It is available on our RUS Copernicus YouTube channel. And there you can see how we use the VISAN software combined with HARP, which is part of the atmospheric toolbox, to process Sentinel-5p data. If you are a RUS Copernicus user, you can request the training kit, and you will get as well a step-by-step guide as with as always with RUS. So just a side note. Okay, other options as graphical interfaces are, for example, Panoply. This is also a very well-known and very well-documented software to process netCDF files. And if you go more into the programming languages, such as what we are going to do today, I am giving you here a very short list of packages or libraries that are available in Python and in R if you are more into R. So in Python, as I said, today we will be using xarray, but of course there is the very well-known netCDF library or the iris module as well. In R, we have the very, very well-known raster package, but also dedicated netCDF packages such as rnetcdf or ncdf. So again, I'm leaving you here all the links so that you can have a look by yourself if you're interested. So now with all the introductions being made, let's move on to the outline of the exercise. So what are we going to do now? Well, first of all, I'm going to show you how to download Sentinel-5p data in case you have never done it. We will then have a very brief introduction to Python and Jupyter. Remember, this is not a Python webinar. The idea today is not to teach you how to write your code in Python. However, I will go slowly through it, and for those of you that are beginners or that are new to Python, it will be very easy to follow. Then I have divided the exercise into parts. The main part, the first main part is point number 3. There I will show you how to process one single level 2 NO2 product using xarray in Python. So we will see how easy it is to import a single product in Python, access the netCDF variables of interest, and then do some basic operations such as filtering the product for quality and doing a geographical subset. The second main part of the exercise is going to be point 4. And there what we are going to do is to run our pollution monitoring over the north of Italy. I will show you how you can process multiple products in Python using xarray, but also using HARP, because we will need to move our data from a level 2 processing to a level 3. And later on, I will tell you what's the difference between both of them. So we are ready to go. Yes, let me go to my virtual machine. So here we have the virtual machine. I've already opened it and I have already logged in. As you can see, if you are new to RUS and to the VMs, the environment is just as a regular, let's say, desktop. It's just that it's sitting on cloud resources. For your information, this is a Linux-based environment. And as you can see, I have a predefined list of softwares that are already installed. So you have Snap, definitely, to process Copernicus data. But also we have development environments such as RStudio or Spider, for example, for Python, or Jupyter, whatever you prefer. This is just a regular, let's say, you can treat the VM as a regular computer. So you have your own and dedicated internet browser. You have your file manager. Sorry, I opened it twice. And so on. So what I mean by that is that the interaction with the VM is the same way as you would do with your regular computer. So let's start, and let me show you how you can download Sentinel-5p products. So the thing you have to do is to go, as always with Copernicus data, to the Copernicus Open Access Hub. Here you will have to go to the Sentinel-5p pre-operations tab. So it's true that the mission is already in an operational phase, and this is completely true, but the data are still sitting on a dedicated hub, let's say, which is the Sentinel-5p pre-ops. But do not confuse that with the mission status, which is already operational. So if we click here, we will access the standard and regular interface in the Copernicus Open Access Hub. So we just need to do as always, let's zoom in into our study area in this case. And as I said, it's going to be the north of Italy. So we can just draw our study area. And then we need to define the parameters for our search. So the first thing you need to set is the sensing period. So in this exercise, we're going to be comparing data from March 2019 to versus March 2020. So we will set the period. I will show you how to do it for March 2019, and later on you can do the same for 2020. So for example, I can go to 2019, March the 1st, and then again 2019, March 31st. Then of course we have to click on the Sentinel-5p mission to activate it, and then the main parameter that you have to set here is the product type. So you know already from the slides I was showing at the beginning, we have the level 1B and the level 2. In this case, we are interested in level 2 and more in particular in the NO2 product. So with this being said, the other parameters you could set, they are not completely mandatory, but just for you to know, is the processing level, so level 2, and the timeliness. So since it's a product that is level 2, NO2, we will select the option offline. With that, we can, of course, log in using the guest account, and then we just click on search. So the main difference, if you are coming from Sentinel-1, 2, or 3, that you will see when exploring this data is that you are downloading full orbits of the satellite. So in this case, the data is not, let's say, cropped to tiles like in Sentinel-2, but we have the full orbit. And as you can see by the footprint of these layers, it is quite massive, right? So you can see here we have 48 products. And here the question can come, why if Sentinel-5p data, or why if the Sentinel-5p mission has a daily revisit time, why do I have more products than days during the month of March, right? I mean, at the beginning I said it has a daily revisit time. So what's happening here? Well, it's a very valid question, and the answer is that if you remember my animation, and maybe I can show you, you can see that Sentinel-5p has some overlap between the orbits. So if I go back to my video, there you go, should launch now. So you see that while orbiting, there is some overlaps between the orbits, and depending on the latitude you are, so the more you are to the north or to the south, or the further you are from the equator, the overlap will be greater. So you can see that in some areas, the coverage by the satellite is twice. So that's the reason. So let's go back to my VM. So how would you proceed for the download? Well, basically, and as for the other missions, you would just click on this arrow to download the product, right? So just download, and it would trigger the action. So of course, and as you can see, those are 48 products, and then we would have to do the same for March 2020. So you can see it's a massive amount of products. Of course, you can download them manually, but I would recommend you to try to automatize this data download process with some kind of script, because if not, you're going to have to click like 100 times to download the data for 2 months in one study area. I'm not going to show the automatic download via scripts from the Copernicus Hub because the webinar is already too extensive with the Python code, but we can leave maybe this for the Q&A session or maybe for an upcoming webinar. So let's imagine I have all my data already downloaded, which I have done in advance, and I'm going to show you my my folder structure for this exercise. So I have everything related to this exercise in my training kit, which is in the path shared training ATMO01 monitoring pollution _ Italy. And basically in the original folder, you can find all the data. So as you can see, we have 43 items. Sorry, not 43, 93 items. Quite heavy data set, almost 4 gigabytes. And as you can see, let me show you. We have the products from the 1st of April, 1st of March 2019 until the 31st of March 2019. So 46 products for that period. And then we have the data set for March 2020. In this case, again, 46 products. So this is the data we are going to use for the last part of our exercise, where I will show you how to process a lot of files in Python using HARP and xarray. However, for the first part of the exercise, where I want to show you how to just play with one single product in Python, I will use a near real-time product. And just to show you the difference between near real-time and offline, so you can see both at the same time. So this is my data, my original data. Of course, in my processing folder, I will be saving all my outputs, and in my aus data folder, I have, as you can imagine, auxiliary information for this exercise. So we can start the exercise, and for that, let's launch the software we're going to be using. So today, as I said, we are going to be using Python. In the RUS virtual machines, you have already pre-installed Anaconda. So what is Anaconda? Anaconda, for those of you that are new to Python or to programming, Anaconda is just a free and open source distribution of the Python and R programming languages. And this is mainly for the scientific computing. And the main objective with Anaconda, if you compare it to, let's say, a regular Python download, is that it helps you to simplify all the package management and deployment. So in the RUS Copernicus VMs, Anaconda is already installed, and you can access it. You can access Anaconda either via command line or either via its graphical interface. So just for you to know, if you type anaconda/navigator, you can launch the graphical interface of Anaconda. And let me just show you very briefly what you can find. There it goes. Okay, so what you will find when you open Anaconda Navigator for the first time is that it comes already with the distribution of Python and R. But on top of that, it gives you the option to install or launch specific applications that will help you to develop your processing scripts. For example, you have RStudio if you're into R, but also you have Spider and other development environments. Today, we are going to be using Jupyter, a Jupyter notebook. More precisely, we will be using Jupyter Lab. Jupyter Lab is just the new version or the new evolution of Jupyter Notebook. And Jupyter Notebooks are very well known within the scientific community because it's a very nice way to share code with others. So the Jupyter Notebook is an open source web application. So it runs on the web that allows you to create and share documents that contain code, equations, visualizations, and narrative text. So you will see now once we open the notebook, but basically you can combine text, images, videos together with active code cells that you can run to process any data. So just another overview of the notebooks, because I think it's very important for you to understand what it is. Notebooks or notebook documents contain both computer code, for example, it can be Python or R, and rich elements such as paragraph, equations, figures, links, etc. And the notebooks are documents that can be both read by humans, but at the same time contain the code cells that can be read by the computer. So the other aspect about Anaconda is, of course, its ability to manage the packages. So maybe you don't know, but when you install Python for the first time or R, for example, the basic installation doesn't come with everything you can do in Python. So you have to install what's called the libraries, the modules, the packages that contain the specific algorithms for the specific tasks. So depending if you are working in Earth observation or if you are working in, I don't know, in other sector, in the bank industry, you will have to install and load different modules. And usually when you run a project, you want to have all the relative packages into an environment so that you have all the versions and everything controlled. So in this case, I have created a new environment that is called RUS, where I have installed all the packages that are necessary for this exercise. So what we are going to do is to launch JupyterLab from this RUS environment where I know that I have all my packages installed. And how to do that, I'm going to show you how to do it in the via the command line. So to launch the JupyterLab in the right environment, the first thing we have to do is to activate that environment. And for that, we write conda activate and then the name of the package, in this case, RUS. Once this is done, we can just write JupyterLab, and the web application of JupyterLab will launch. So let's wait for it. Okay, there it goes. I am just going to go full screen so that we have a better overview. Okay, great. So here is the notebook we are going to be using. Here's the notebook we are going to use today. So actually I had already opened, but when you open JupyterLab for the first time, this is what you will see. What you have to do is go to your browser here within JupyterLab and navigate to the folder where the notebook has been stored. In this case, my notebook is stored in the path of my exercise, so share training ATMO02 monitoring pollution Italy aux data. So within the aux data folder, you can find in this exercise the Jupyter notebook we are going to be using today. So I'm going to close this. So again, remember, so the objective of the exercise is going to be the analysis of the pollution over the north of Italy in March 2020 versus March 2019. So let's get started. If you are repeating this webinar, if you are rewatching this webinar and you are not in the live session, it might be interesting for you to go through this text that is here. But this is just basically a repetition of what I have said in my slides. So it's just for you to know. So let's go down and let's see the structure of our exercise. So what we are going to do, and this is just again for repetition, we will first of all, of course, load the Python modules we need. We will then explore the one single Sentinel-5p product using xarray. We will do some basic operations, and for this we will be using a near real-time product, and then we will do the multi-temporal analysis using HARP. So as you can see, the Jupyter notebook contains text links. For example, here I'm leaving you some links for some Python tutorials and Jupyter notebook tutorials. But at the same time, I can have my my cells with code that I can run. And how do you run a cell or a code cell in Jupyter? It's very easy. Either you select the cell and you press Control Enter, either you go and press the play button, or either you go and press run selected cells. As you can see, there are more options to run. But anyway, let's move on. So the first thing we do is to of course, we are all assuming that the libraries have been already installed. So what we do is to load and import those libraries into our Jupyter notebook. So the thing I want here to highlight for those of you that are new to Python is that when you load or when you import a library, you can do it, for example, here I'm importing the xarray library, but at the same time I'm saying import xarray as xr. And this is I'm just defining an acronym that I will use later on in my code, so that instead of writing xarray dot and the function, I will only have to write the acronym, which is a little bit shorter. So some libraries have some kind of standard. Let's say, for example, pandas is usually abbreviated as PD, NumPy is always abbreviated as NP, etc. So let's go to, so we have everything loaded. So let's go to the next cell. In the, if you are repeating the exercise again, you will find here again the same explanation I've made in my slides, so we can skip this because we know already what this figure means. And actually what we are going to do is have a look to this folder structure, this file structure. So how do we do that in this exercise? So the first thing we are going to do is to define the path, the folder where we have all our products stored. Remember, I showed you a couple of minutes ago, all our data is in the shared training ATMO02 blah blah original folder. So first of all, we declare the folder where our products are. Then I'm going to create a list that contains the path to every single of those files. And here I'm creating a list for the offline products, and then I'm creating another list for the near real-time products. Remember, I have only one near real-time and many offline products, right? Okay, once those lists are created, I'm just printing them to see the output. I'm actually printing the length of the lists. And then I am creating a Python variable that is going to be called s5p underscore file, which is pointing to the first element of my list that contains the near real-time products. And I'm just printing that. So let's run this. Oh, sorry, I pressed the wrong key. Let's do like that. So what's the output of this cell? What it's telling me is that I have 92 products, 92 offline products. Remember, 46 for the month of March 2019 and 46 for the month of March 2020. Then I have one near real-time product, which is the one I'm going to use in this part of the exercise. And then I'm just printing a confirmation that it's telling me that the product that I'm going to analyze right now in this part of the exercise is in this specific location, in this path and with this name, right? So this is done. Now let's go to the following code cell. So what we are going to do is to actually open this dataset in Python and have a look. So this is done very easily. The first thing we do is sorry, let me highlight while I explain. The first thing we do is we call the xarray library because we need one of the functions of this library, and we do it by writing its acronym, so xr. Remember we said import xarray as xr, right? So we call the xarray library, and then with the we call one of the functions of this library, which is called open dataset. So we say xarray open the dataset, and then we point to that dataset. And here I'm just calling the variable that I created before, pointing to the file that I want to analyze now, right? And then I'm going to save all this into a Python library, into a Python variable that is going to be called s5p underscore image, img, underscore GA. GA stands for global attributes. So by running this line, I will access the global attributes of the file, which I'm going to print in the following line. Then we will have a look to the metadata group. But we will not have a look to the metadata group, but to the a subgroup that is within the metadata group, right? If you remember, if you remember here, you can see that the metadata, a little bit more up, within the metadata first level group, I have second level groups, right, that I can access in Python. So let's have a look how you do that. So we basically do the same. We call the xarray library, we call the open dataset function, we specify the file that we want to open, and then with the key parameter group, we specify to which group we want to go. In this case, we want to go to metadata and, for example, the granule description. All of this, we will save it into a new Python variable that is going to be called s5p img mt for metadata. And then we will just print this variable to have a look. And the last thing we're going to do here is to do the same for the product group. Remember, the product group is the most important one for us because it is there where the actual measurement is. So we do the same, xr open dataset, and we save it into the Python library, into the Python variable s5p image prd for product, and then we print it. So let's run this and have a look. So I go down a little bit more. Okay, so what do we see here? Well, the first thing is the global attributes that we were opening. As you can see, I have, since this is a netCDF file, which has been opened as an xarray dataset, so now we have a xarray dataset object, and as this is a netCDF file, we have dimensions, we have variables, and we have attributes. However, here there are no dimensions, no variables, no coordinates. Why? Because at this level of the product, we are in the global attributes. The only thing we have are attributes. Remember, attributes equals metadata, to make it simple, right? So what kind of information do we have at this level? Well, you can see it. For example, the idea of the product here. You can see the orbit. What was the orbit number? You can see, keywords. You can see the creation date, etc. And now the question is, okay, nice, but some of this I understand. For example, source is pretty obvious what it means, but what is, naming authority? Well, this, for example, this. I mean, what I mean here is that by looking into the product user manual that I was making reference to before, so let me show you my slides here. By reading this document, you will see the full description of all those attributes and about everything on the file. So again, I recommend you to go to this document. I will insist several times and read it if you want to get the full picture of the data. Okay, so those are our global attributes, nothing very exciting so far. Then we accessed the metadata, the granule description group within the metadata group. And again, here we have only attributes, so metadata, right? Processing mode, processing level, etc. So information that, okay, good to know, but not actually the measurement we want. Again, if you want to know the full description of this, go to the product user manual. And then finally, we access the product group, which in this occasion, we can see it has dimensions. Remember in my presentation, this slide, dimensions, variables, attributes, coordinates. Well, now this makes more sense when you can see that in the file, you have dimensions, you have coordinates, and you have variables. Once we access a variable, we will see now the attributes. So this is the first overview of the product, and now you can tell me, well, Miguel, this looks great, but I don't see anything. I don't see any measurement. I don't see any image. Let's say this is Earth observation, and you're right. So what we have to do is to actually access the information. So far we've seen a lot of groups, metadata, attributes, and whatever, but we want to see the measurement, the geophysical parameter that has been derived from the measurements of the satellite. And where can you find that? Well, within the product group. So within the product group here, you can see that we have variables. And remember, in netCDF, the variables is what contains the data. So they are used to store the bulk of the data, right? So in the variables of the product group, you will find the, for example, tropospheric column, which is the one we are going to be using in this analysis. And how do you access that? Well, let's go to our following code. What we are going to do is we are going to create a new Python variable that I'm going to call NO2, and this is going to point to my netCDF file product group. Remember the variable we were using before, so we are saying here the NO2 variable is pointing to my netCDF file group product, and within the product group I'm going to access the variable nitrogen dioxide tropospheric column, and this is the syntax you have to use. So it is like that you access a variable. It is like that you access the variable that contains the measurement, in this case the geophysical parameter. And since this is a CDF file, remember we can access we are going to print the dimensions, the coordinates, the attributes, and the values or variables here. So let's run it and have a look. So finally we have reached our measurements. Again, we have specific dimensions for this variable, in this case time, scanline, and ground pixel. Scanline and ground pixel makes reference to the coordinates, so the of the image, so the x and y. Of course, this is a geolocated product, so the latitude and the longitude. You can see it on the coordinates. Then we have the attributes of this variable, which are, as I said, metadata of this variable. For example, we see the units of the measurement. They are provided in moles per mole per square meter. We see, for example, the standard name of this variable, or the long name, or whatever. And one key attribute I want to point out here is the multiplication factor. So this attribute here, this piece of metadata, is going to allow us to convert the data from its original units, from mole per square meter, into other units, for example here, to molecules per square centimeter. And then if we access the values of my NO2 variable here, we can see the actual measurement. So this is actually a NumPy array that is holding the values. And if you are a little bit familiar with Python, you know that as far as you have a NumPy array, then you are ready to go. You can do, let's say, regular Python manipulation of the data since you have a NumPy array, right? So this is very good that this package gives you the data in this format. So now here's the measurement. Here is my tropospheric column of NO2, and of course you can tell me, well, this again, Miguel, looks very nice, but it doesn't help me at all. What I would need, or what I imagine you need, is to plot this data somehow, right? So let's go now and see how you can very easily plot this data in Python. So what we are going to do, and this is not mandatory, it's just for you to know, we are going to convert the measurements from their original units, which are again mole per square meter, into the molecules per square centimeter. And why is this? Just to give you a little bit of context, the units that are used originally in Sentinel-5p belong to the International System of Units. So in this case, for an integrated column value, this means mole per square meter. However, traditionally, integrated columns are measured in molecules per square centimeter. So you can easily move from one units to the others by using the multiplication factor. And how do we do that? We just overwrite our NO2 variable, and this is important. Pay attention here. We are overwriting. So if you want to go back to the original values, you would have to re-import the product. This is not how you have to do it. This is just how I do it. It's just a way to proceed. So I overwrite my NO2 variable, and I say that NO2 is now equal to NO2 times the multiplication factor. So it's not that you multiply by the number, but we specify that in this way. Okay, and then we just plot it. So during this exercise, we are going to create different plots. I'm not gonna go through the code that plots the data because I don't think it's that relevant. You can do your plots if you have some experience with Python in your own way, and you can follow your own preferences. So I will not go deep into that. The only thing I want to mention is that we use the p color mesh function from matplotlib, which allows to plot irregular data. So let's have a look at the data. Remember, we import the product, we multiply by the multiplication factor, and we plot it. So let's have a look. So this is then the first time we are looking at the data, and the plot is, it's good. There is information here. For example, we can see the latitude and the longitude on the y and x. So you can see a little bit the patterns in the concentrations, the different values, etc. But I would say from my point of view, it is not very helpful because it doesn't help us a lot to locate the measurements into a geographical area, right? I mean, of course, we have the lat and long coordinates here. So if you know, for example, where your city is, well, you can basically, for example, Rome is in 11 and 42. So I know Rome is over here. But okay, it's not the best way to do, right? It's not very scientific. So of course, we can produce a better second plot. We can produce another type of plot using a dedicated Python library that is used to produce better visualizations of the data. So I know I said I was not going to go into the code that makes the plot, but actually here I will, and I will explain you why. So let's run this code here. Remember, here we are not touching our data. We are just showing it. We are just creating visualization and a display. So I'm saying that because you can do it the way you want. Let's first analyze my plot here, and then I will tell you how you can make some modifications to it very easily. Okay, so here we have the data. We see we have added a dedicated title. We have added some background information, for example, the coastlines, so we see a little bit where we are, the scale bar, and some grids of the projection. So this is Cartopy. This is a Cartopy visualization, and again, one of the good things of Cartopy is that it allows you to create projected visualizations, let's say. Again, I'm leaving you the link to this library here if you're repeating this exercise, so you can have a look. So one of the nice things of Cartopy is that you can change your plots very easily. For example, I'm going to show you. Let me put it like this. For example, here we have added what's called in Cartopy a stock image. It's just a background image to put some context. If I comment this line and I run my code again, you will see that now the plot is displayed without any background image, right? So if you prefer an image without any background information, then you can leave it like that. For example, we can remove the grid lines. So we can just do the same. We comment the line so that it's not executed by the kernel, and then we get the image like that. You can see here I have added the rivers, the main rivers, which I could remove by commenting this line. Or for example, I could select the option set global, which will plot without taking into account the extent of my product. So in this case, we are using an orthographic projection, and as you can see, this is creating this kind of plot where I have the Earth, let's say, as a globe, right? It's not like projections like I don't know, like UTM or so. So this is up to you. You can play with this code as you want. In my case, I prefer to not have the global option selected, to add some background image, some grid lines, and the rivers. So let's run again, and There we go. Also, I have added to the plot some points of interest just to locate our product. So I've added Rome. I have also added Milan, and this is the area where we are going to focus. But I've also added, for example, Madrid, where we can see it's kind of a hotspot in this image here over Spain. So now that we have a second and a little bit more advanced visualization of the data, we can move on and do some basic operations. So one of the main things you have to think when working with Earth observation data, I would say in general, is the quality of your measurement. It's not that you can take it for granted. Of course, there is a heavy work done by ESA to ensure the quality, but there are some conditions that might happen in your target. I'm thinking about the condition of the atmosphere, if it's cloudy, that you cannot control, and this will destroy the quality of your data. So the quality of the individual observations depends in Sentinel-5p on many factors, including cloud cover, surface albedo, presence of snow ice, saturation, geometry, etc. So these aspects are taken into account in the definition of the quality assurance value, which is available for each individual observation, meaning each pixel, which provides the user with an easy filter to remove less accurate observations. So the QA value is a continuous variable ranging from 0, which is error, to 1, which means perfect. And you should use the filter, as you can see here, in two ways. Either you apply a filter larger than 0.75 or larger than 0.5. It is recommended to apply the 0.75 because it removes cloud cover scenes and partially snow ice cover scenes and errors and problematic retrievals. So the 0.5 filter is also okay. It also removes bad quality data, but it also would imply a different processing in terms of averaging the values, but let's not go into that. I would recommend you to use 0.75 so that you are sure you are using the pixels with the better quality. So let's actually visualize this quality in our product, and let's see what happens when we filter the image. So how do we filter actually? It is very easy. We are doing it here in this line. We are saying we are creating a new Python variable that's called NO2 filter, and then we are saying that I want to filter my NO2 product wherever the quality assurance value, so wherever the quality assurance value is bigger than 0.75, right? And then we just plot. So this code here is just a plot. So let's move on. So let me go down, and here we can see the plot. On the left side, we have the quality flag layer. So the pixels are classified from 0 to 1. You can see that most of them have good quality. Some areas over here have less than 0. They are around 0.4, right? When we filter our image with the code I showed you before, this is what we get. So as you can see, when you work with Sentinel-5p and you apply the quality filter, it might happen that the observation that you had that day for your area is not valid at all, and you have to wait for the next day. That's why making multi-temporal analysis makes more sense, because then you can make sure that at least you will have some observations throughout time that are valid. As you can see, we were interested in north of Italy, and we got no data. So nothing to do there. Of course, you can lower your threshold, but of course you are assuming you are taking some risks. By the way, in the code, we are automatically saving the plots by using this line here, which will automatically save a PNG of this visualization so that you can share it with your colleagues or include it in your reports. So the last thing I want to show you when processing a single file is how to do a geographical subset. So this is something very easy in xarray. You just need to define the coordinates of the lat-long coordinates of your study area. In this case, I'm defining the upper right lat-long coordinates of my area of interest and the lower left coordinates. And then again, I use the where function. So I'm creating a Python variable called NO2 subset. And then I say my filter product, which I saved in the variable NO2 filter. I want to do a subset, and I say where. So I say where the filter product has a longitude that is lower than the upper right longitude, and at the same time has a longitude that is bigger than the lower left longitude coordinate, and so on. It's just a basic operation. So in that way we filter and then we plot. So the code here is just making the plot, and at the very end I'm saving again this as a PNG in the processing folder. So let's run it and have a look. Okay, so that's how we make the subset. And as you can see here, I did my subset over Madrid, and well, that's the result. Very easily you can produce those subsets and, let's say, zoom into your study area. And in this case, we are processing only one single product. Okay, so let's move on to the last part of the exercise, which is going to be the multi-temporal processing of Sentinel-5p. So it is actually here where we are going to run the analysis over the north of Italy. So how are we going to do that? Well, let's first talk a little bit about HARP, which is the software we are going to use. You know already, and it's written here on the Jupyter Notebook, HARP is part of the ESA Atmospheric Toolbox project and aims, which aims to provide scientists with tools for ingesting, processing, and analyzing atmospheric remote sensing data. So HARP is a toolkit that will allow us to do this pre-processing. It has a command line set of tools, but it can also be accessed via the Python interface, which is what we are going to do today. And by appropriately chaining calls to the HARP command line tools or via Python, we can pre-process satellite data so that it can be compared and have a same temporal and spatial grid. And this is the key part, to have a common temporal and spatial grid. So we are using HARP because we need to generate level 3 products. Level 3 products means that our level 2 NO2 product is going to be resampled into a common grid. A common grid that will have an equal pixel size, because by default the pixels of Sentinel-5p are not equal throughout the swath, because we are using because of the characteristics of the optical sensor we are using, right? And the very large swath of 2600 kilometers. So in order to have pixels with the same size, we need to, let's say, create a new, let's imagine an empty raster where we define the size of this new raster, where we define the pixel size of this raster, and where we transfer the information of the original pixels to this new raster that is obviously projected. So this is what is going to happen. And this we do using HARP. If you want to know more about this, in the previous webinar, which I mentioned here, let me show you, sorry, it's here. In this webinar, we went through this processing using a graphical interface as well. So if you're interested in that, you can watch another explanation on this processing in this webinar. So how do we do this level 3 conversion? Well, the first thing is I am defining an output folder where I'm going to save my outputs. So just run this. Then I'm going to create a for loop where for all the files I have identified in my variable, which contains a list of files. So this variable here is just pointing to all my files in the original folder. Remember we created at the beginning. And we are going to say, for every of those files in my original folder, I create a Python variable which is going to consist of, first of all, we call the HARP library, and within the HARP library we call the import product function. And then we say for I, so for every element of my list, I'm going to run a set of operations in HARP. So the first thing we do is we filter our data for the quality, so everything above 75. Then we convert our units to molecules per square centimeter. Then we create a new variable that is going to be called time stop, date time stop, which is going to allow us to have the range of the measurement, so from the beginning of the sensing to the end. And this is only to help us in the data analysis. You could skip this step if you want. Then we do a subset to our study area. So if you see here, I'm defining the latitude and longitude of my study area. So it's going to be between 43.6 degrees north and less than 47.2 and so on. And then comes the key operation in this set of operations, which is the bin spatial tool. So pay attention here because this is the key part. What you want to do here is to define this spatial grid, this kind of new raster where you are going to resample the data. And you do so by defining the properties of this new grid using the lower left corner as reference. And I repeat that, the lower left corner. Pay attention because if not, you will spend a lot of time trying to figuring out this. So pay attention here, we have 6 numbers. We have 3 numbers here and then other 3 numbers. What do they mean? What I'm doing here is, first of all, I am in the second position, I am defining the latitude coordinate of my lower left corner of my grid, right? So we have our study area, let's say our study area, which starts at 43.6 latitude north. Then we have to define a resolution for that grid, which is going to be defined in degrees. So in this case, 0.01. And then you have to define the extent of the grid in latitude. So we define that here with this number. So it doesn't mean 360 latitude, that doesn't make sense. What we are doing is 360 multiplied by the resolution, which is 0.01 equals 3.6. So 3.6 plus 43.6 will give you the extent in latitude, which is going to be 47.2. So this is the logic behind. And again, we do the same here for the longitude of the lower left corner. We do 7.6, which is the lower left longitude coordinate, and then we define the extent in the longitude direction by defining the resolution, 0.01, and then the number of steps. 610 multiplied by 0.01, it's 6.10. If you do 7.6 plus 6.10, it will give you 13.7. Okay, then we just derive the central coordinates of the pixels, and then we define the variables that we want to keep as output in our product. So once this is done, we would save that product into our processing folder here with a specific name. It's going to be the same name as the input, but we only replace the level 2 in the original name by level 3. And then we just call the HARP export product function, and we just save it as netCDF file. So I'm not going to run this because it would take, it takes like 20-30 minutes. So I'm going to avoid it, but I want to show you that you can actually see this very easily. Let's see if I manage to show you. So if I go to my processing folder, you can see that here I have done this already, and I have a lot of files, in total 96. And you can see that they have the same name, but here I have changed, for example, level 3, right? You see level 3 all over around. Okay, so let's move on. Now we have all our products regridded into a common spatial grid. And now we just need to do a few steps to see our final analysis. The first thing we're going to do once we have preprocessed our data into level 3 is to extract from the product name the time coverage start and time coverage end. And we do this here. Why do we want that? So I'm showing you here an example. So for every single product, we are going into the attributes of this product. So here we go into the attributes, and more in detail we go into the specific attribute we are interested on, which is the time coverage start and end. And we store that information in order to allow us indexing of the products based on time. So this is done here, and now we are ready for the multi-temporal analysis. Here. Okay, so let me run this and I'll explain you what's happening. What I'm doing is I'm telling in Python, okay, I have my level 3 products processed by HARP, and they are in this path, in the export path I have defined before, and they should be named something that contains level 3 NO2. So I create a list with those names. And then what I'm going to do is create a new Python variable here that is going to be equal to the import of this data. So I call the xarray library again, and I call a dedicated function to open a list of files, which is called open_mf dataset. I provide as input a list of files, in this case file name level 3, and then I say combine nested. This is going to create a stack of files, and the files are going to be stacked along the time dimension to allow time indexing. And how is this time dimension created? Well, we do it using this preprocess function. Preprocess function that is defined here on top. What I do is for every single of the files that I have created in HARP, I create a, so what is being done is that we create a time dimension, and we create that time dimension by accessing the time coverage start value that we extracted before in the previous cell. This will allow us to create this time dimension that will allow at the same time us to stack the products over time. So as you can see, I have a netCDF file that has been combined, and I have 92 products, remember. And sorry, and they go, if you see here, this time dimension, they go from 2019 March the 1st until 2020 March 31st. So you know already we have the two full data sets for March in both years. You can see the different data variables that we have kept. And with that being said, now you can tell me, well, that's good, but what I want to do is to produce the analysis for 2019 and 2020 independently. So what we are going to do is we are going to create two we are going to split the data set in the 2 years, right? So I'm creating here a new variable that's going to call level 3 March 19, which is going to be equal to the previous one, so level 3 March 1920. And here we are going to do a time slice. So we are going to select only the files that are between the 1st of March 2019 and the 31st March 2019. Then we will do the same for 2020. You see here the name of the variable is very similar, but ends in 20. And then the question is, what is this line for? Well, if you remember, per month, I didn't have March has 31 days, but I didn't have 31 products. I had more. Why? Because this overlap of the orbits, right? So what I want to do is to keep one single file per day. And I do that by averaging the files that belong to the same day. And this is what I do here with this line. I'm just doing a resample over the time dimension. I only want one product. I am doing the mean over the time. So let's have a look at this. And what you can see here is the data set for March 2019 and the data set for March 2020. Basically, it's just the same, but now we have one product per day, and I have split the data sets in the 2 years, in the 2 months of the year of 2019 and 2020. So you see, along the time dimension, now I have 31 products, so 31 days for both. And you can see the confirmation here. The 2019 data set goes from the 1st to the end of the month in 2019, and the same for 2020. So now that I have the data split into the 2 months, I'm almost at the end of my analysis. The only thing I need to do is to average the measurements throughout each month to produce, in this case, the mean statistic. So I'm going to create a new Python variable that's going to be called, in this case, level 3 March 19 underscore mean. And what I'm doing is I'm telling Python, look, take my previous variable L3 March 19 and derive the mean value of the files and do it throughout the time dimension. So as you can see, it is very useful to have this time dimension because it allows us to do very logic operations that one would think. If you think about what you want to do with the data, you say, I want to do the average over time. And the syntax here in xarray is very easy to follow because it's pretty much following the logic of your head. Okay, so I do this mean calculation for 2019 and I create this variable here, and then I do the same for 2020 and I create this other variable here. Okay, fine. And once I do so, what I'm doing is I am accessing the tropospheric NO2 column specifically, and I'm saving that into the final variables of our analysis today, which are going to be NO2 March 19 mean and NO2 March 20 mean. And we can have a look to these variables. As you can see, that's how they look like from the, let's say, the first perspective. But of course, we want to have a look and plot it. So what we are going to do as the last step of the webinar is to plot those variables. So here I'm giving you the option to select which month you want to display. So this is interact. I mean, you can just change the script. For example, if you want to plot 2019, just change this. And now we run this cell. And here, this very long cell is just doing the plot. So I know if you are new to Python or you are not familiar with this, it sounds like a lot, but this is just making a plot. I will not go into the details because it doesn't make sense, but it's making the plot. Of course, you can make the plots in many ways. And at the very end, I am saving the plot as a PNG file. So let's have a look. We are having just a warning there, but you can continue. So here is our analysis. We see the final result for the average NO2 concentrations at the tropospheric level, remember, for March 2019 over the north of Italy. So I have added here just a little map to show you where we are in Italy, if you're not familiar with its geography. And here is our study area. So you could change the extent of this plot by going into the bin spatial tool, by going into the HARP processing we have done. So if you want to change the characteristics of your plot in terms of spatial resolution, you can just come here to these 2 lines and change accordingly. And in this way, it would change. Okay, so those are the results for 2019, and we can now have a look to 2020. So I just changed this by 20 and this again by 20, and I just run again and I have a look to the results. So as you can see, the concentration is much lower, and if you think about the situation due to the COVID-19 outbreak, you can imagine why is this happening. There was a massive lockdown in Italy, especially it started a little bit earlier in the north, but it's happening all over Italy and all over the world, I have to say. So this is the consequence we can appreciate from space using Sentinel-5p data. As I told you, I have saved the files, the plots as PNGs. So just as a side note, you can, for example, in Python, create a GIF to actually see that, to see a quick display between the plots. So I'm going to show you the result of that. Let's see if I manage to exit my... Okay, here I am. So I have created in my plots folder, sorry, in processing plots, I have created all the plots basically. So you can include them in your reports and send it to your colleagues or whatever. And in this case, I have done a GIF, so we can display it very easily, even in Jupyter. For example, I can just drop it down here. Sorry, I can first put a markdown cell and then add it here. Okay, so if I run that, you can see the plot. So you can see the large decrease in concentration of NO2 at the tropospheric level over the north. So that's that will be the end of the analysis today. It's a long webinar, but I think we went through the data. We went through a very detailed description of the files, the netCDF characteristics, and the way you can process that in Python. So with that being said, I just want to give you some highlights to end the session. Going back to my slides. So what I want to tell you is as an overview of the webinar and of the situation with the Copernicus program. With the new Sentinel satellites, the challenge in satellite remote sensing is no longer data availability, but rather how to store and process all the information. In addition to that, it is necessary to explain how the data can be used and support users in their applications. The RUS service is here to solve those problems by providing virtual machines to store and process the data, and by offering a dedicated help desk supported by a team of remote sensing experts that can help you in your projects. So before moving into the Q&A session, let me tell you again that you can repeat this exercise by your own if you want to practice or adapt the methodology to your own applications. And for that, go to ruscopernicus.eu, and you can there get your RUS Copernicus virtual machine and repeat this exercise. So let's I will end the session here, and then we can go to the webinar. We can go to the Q&A session, sorry. So thank you very much, everybody, for attending this webinar. I hope you are all doing great, and I hope you have learned something new today about Sentinel-5p, maybe also about Python. You will receive a poll after this webinar, so please fill in the questionnaire. We really appreciate your feedback, and it allows us to improve in the future. Also, if you are interested in more Python-related webinars using and processing Sentinel data, please let us know, and we will try to do it. Okay, thank you very much. So again, thank you very much for joining the session. I hope you have enjoyed the webinar. You have learned something new about Sentinel-5p, about Python, or about any other software I've used. I wish you a nice afternoon. Stay safe in this context, and I will see you in the next RUS webinar. So thank you very much, and ciao.